All right, so let's consider a system that we're going to represent by this box here. It is both linear, and we know what that means, and time invariant. We also know what this means. So I'm not going to go back and then explain what those mean. And let's say that we feed our system a signal x of t. That means it's a signal that depends upon the time. We should get at the output another signal which we're going to name y of t. Okay? Now let's say that we are going to feed our system just a special type of signal, which is the famous delta of t. And the system is going to respond, and we're going to call the response h of t. Now, delta of t is simply the impulse function. And the response of our system to this at its input, h of t, is going to be called simply the impulse response. The name basically is a giveaway. It's the way our system responds to an impulse at the input. Okay? Now, let's say that instead of applying delta at time t, we're going to just delay it by a certain interval. We're going to call it tau. So tau is simply a delay. Now, knowing that our system is time invariant, that means if I put here delta delayed by a certain amount tau, the output should be the same, except that it's also delayed by the same amount. All right? So far, so good. Now, let's say that because the system is linear, and we take this and we multiply it by x at tau, this should also be x at tau. Now, the reason why is that if you take a signal, multiply it by a certain constant, the output should simply be multiplied by the same constant. Right? This is because of the linearity of our system. Okay? Now, let's say that we made tau vary from minus infinity to plus infinity. So we're trying every possible delay from the infinite past to the far future. And every one of these basically impulses at the input multiplied by x, which is the value of the signal x of t, all right, at time tau. What we're going to do is we're going to take all of these, all right, and multiply them by x of tau, and also by a constant d tau. Right? So I took my delayed impulse, multiply it by x at point tau, time tau, delay tau, and this is just an interval tau. This is basically a very small interval of time. If I feed this to my system, again, because it is linear, I should get the response to delta delayed by tau timed by x at point tau times by an interval d tau. Okay? Now again, because my system is linear, I can take all of these and add them up and let tau basically vary, let the delay vary over an infinite range of possibilities. So this is what I'm doing. I took the delay that I applied to delta, all right, and I let that tau vary from minus infinity to plus infinity. I'm trying basically every one of these, all right, so x of tau times delta t of minus tau multiplied by d tau and simply adding them up because an integral is nothing but an infinite sum. If I feed this to my system, because it is linear and time invariant, I should get in here h of t minus tau times x at point tau times interval d tau, And since I am trying every one of these and adding them up by allowing tau to go from minus infinity to plus infinity, this is what I would get. Again, this is because it's time invariant. This is because it's linear. This is because the system is linear. And this infinite sum is also because linear. All right? Now, delta of t is an even function, which means delta of t and delta of minus t are the same. To convince yourself that this is the case, just draw delta of t over t, and maybe we can use a different color in here, maybe something a little bit thicker. And you're going to see that here's delta of t. It's obvious that this is a function that is symmetrical across the vertical axis, which basically proves the point. All right. Okay. Now let's just make this brush slightly bigger. All right. So where I have delta of t minus tau, I can replace it with delta of tau minus t. That would give me the same value. So that integral from minus infinity x of tau delta of t minus tau d tau is the same as integral minus infinity to infinity x of tau times delta of tau minus t d tau. All right, and that integral is integral from minus infinity to just to the left of t x of tau delta of tau minus t or t minus tau, it doesn't really matter, d tau plus integral just to the left of t to the right of t x of tau delta of t minus tau or tau minus t, wouldn't really matter, plus integral from just to the right of t to infinity x of tau delta of t minus tau d tau. Now, this function is equal to infinity when tau equals to t. To the left of t, this is equal to 0. Oops, not here. Here. To the left of t, it's equal to 0. To the right of t is equal to 0. And exactly at tau equals t, this should be equal, integral, just to the left of t, to the right of t, x of t times delta of t minus tau or tau minus t times d tau. Now, this doesn't depend upon the dummy variable tau, so we can take it out of the integral. So I got x of t integral to the left of t, to the right of t, of delta of t minus tau d tau. And by definition, this integral equals 1. So that long integral from minus infinity to plus infinity x of tau delta of t minus tau or tau minus t, again, this doesn't really matter since it is a even function, is simply x of t times 1, which is simply x of t. Now this is an interesting result here. I mean, it took us a long time to get in here, but you're going to see that it's worthwhile, all of those mathematical steps. So if I were to go back to what I had originally, I had my system. Oh, I should put it a little bit to the right, not exactly here, maybe here. All right, so this is my system, and I fed it integral minus infinity to plus infinity x of tau delta of t minus tau d tau. And because of my system being linear and time invariant, it gave me integral from minus infinity to plus infinity x of tau h of t minus tau d tau. Well, it turns out that this is nothing but a weird way of saying it's x of t. And since this is fed into my system, I would expect the output to be y of t. So I can write y of t as being this. All right, now moving on. This integral in here, so we can simply put it that x y of t is my integral from minus infinity to infinity x of tau times h of t minus tau d tau. All right, well, this is an interesting result, but let's just dig a little bit further in here. Well, this integral basically was so useful to mathematicians and to scientists and engineers in general that it even basically got a special symbol. This is simply what mathematicians call convolution. So, to find a signal y of t in response to an arbitrary input x of t, all you need to do is take that input x of t and then convolve it with h of t. And if you recall, h of t is nothing but the impulse response. Now, the problem with this convolution business here, I think I scrolled too much. The problem with this convolution of x that is fed at the input, this is x of t going into my system, and my system outputting in response a signal y of t, is that this integral is a little bit too complicated to handle, generally speaking. Right, here's the integral. In fact, I should just frame this. It's a very important result. But we're going to try an interesting thing in here. We're going to take y of t, and then we're going to see what happens when we do the Laplace transform of y of t. So it's Laplace transform of x of t convolved with h of t. All right. It turns out that Laplace transform, although I didn't prove it in here, and I will not prove it in here, but you can browse the internet and then look for proofs. There's tons of them online and even on our textbooks, I think. It turns out that the Laplace transform of a convolution is simply the Laplace transform of x of t times Laplace transform of h of t. So basically the Laplace transform converts a convolution integral into a simple multiplication. So this is a very, very interesting result here. Doesn't look like it, but this is an extremely useful result. Now let's call Laplace transform of y of t y of s. Let's call Laplace transform of x of t x of s. And let's call Laplace transform of the impulse response h of s. Well, now we're onto something very, very useful. H of s, which is the Laplace transform of the impulse response, has a very interesting name. It's called the transfer function. I'm going to stop the video in here because YouTube only allows, I think, about 15 minutes worth of recording to be uploaded, and I'll continue this in just a minute.